Hello.
Hey.
Yeah, thanks for coming. Yeah, apparently not a lot of people, but that's fine.
Yeah, a bit not a crowd.
Yeah, I mean, I know this is just the topic that might interest a few people, and also, yeah, I'm aware I really have to work on my presentation skills, but I think we can, at least I can show what I have, and that's good. So maybe wait, like, I don't know. Oh, it's 4:05 now, so let's wait one more minute and then yeah, let's start. Until then, I will just try to share my screen and yeah, so let's just do a slideshow. Okay, wait, no, I just okay. Can you see the slide?
Yes.
All right. Okay, I think yeah. Let's just I will go through this and yeah, I think I will present this multiple times anyways. Let's just yeah. Okay, so now I just like figured out the details of this new thing I want to propose, and I think I managed to make it even simpler. And yeah, so the basic thing is the basic structure that I want to show is it's I just call them index tables, and so these are yeah, and I will have some drawings that will show it better, but these are an ordered list of events, and one event can be a block hash, a transaction hash, a log address, or a log topic, and this is all tree hashed, and I will also show why how that can be used for searching and proving. And so one important thing is that an index table is generated either from a single block or a number of blocks, but they are always generated when like those blocks are finished, uh, and they are not. These. Uh, and the new tables are generated from new blocks, and since these are just sorted lists, they can be merged together. So that's how this structure evolves. The complete table is never modified. If the chain is rolled back, then some tables might be discarded and regenerated. But yeah, those are just small tables at the and also yeah, okay, let's just so this is a this is a chronological order of events in an example. And yeah, I have this I have few events, like there are four. So this is an index table that covers four blocks, and there's there's some empty blocks. There's a block when there's a transaction with two log events, a WA transfer and a USDT transfer, and then second transaction with a withdrawal, and another block with another USDT transfer. So this is just uh, enough for some simple examples. And yeah, as you can see, now this is the chronological ordering. So this is not how the table is hashed. So here, every entry has a block number, transaction number inside of the block, and log index of the log inside of the transaction. And each entry has a type and a value, which is 32 bytes. And the way the table is generated is that it's sorted. And here I also reorder the columns so that it represents the sorting order. So it's sorted by event type first, and then by value, and then by block number, and yeah, so the position. And the whole thing is tree hashed. Uh, the way I imagine it now, probably the easiest thing is just use the SSZ list hashing. So, uh, and since this is an immutable thing, and we know like in advance the number of items, so we can just create a list with an appropriate capacity. So this list has, yeah, I guess it has 5 levels of nodes, and it has a total capacity of 32 items, but now we have 22. So if we have more than 22, more than 32 items, then we are going to have a more tree levels. And yeah, uh, uh, and uh, and the individual items. So now maybe this could be optimized, but the way I imagine it now, we can just have a 64-byte encoding. We don't necessarily need 64 bytes, but yeah, we need more than 32. So it's going to be two nodes in the binary Merkle tree anyways. And I think the nicest way probably is to use an encoding where the numbers are big endian. I mean, the event type is not really relevant because it's 1 byte, but maybe later we can have more event types for some reason. Anyways, but the position numbers are also encoded in big endian, so the whole thing can be just lexicographically ordered the same way it is hashed. And yeah, maybe if the yeah, this looks probably simple enough. And yeah, in some cases the transaction and log index is not applicable because we have entries for the block hashes themselves. There's then no transaction index, and also we have entries for the transaction hashes, then there's no log index. So these are just left as zeros in the encoding.
Um, could we represent them with something else, and then we don't potentially need the type, right? If we have like optional or a null or whatever.
So what I don't understand.
Okay, so potentially we could infer from missing data on the transaction and log columns the type of the row, and then we don't need the type
Uh,
column.
maybe we could. Well, actually, we could. Yeah. So we could do that. We could have uh, another column which could be like the topic index inside of the log, and then probably and yeah, we could use some other value instead of zero for the missing entries. And yeah, so this would tell all the necessary information. But I mean, this is not about some tight encoding. This is or this is just for hashing. It doesn't have to be optimal. And also the important thing is that it is sorted uh, by type first and then by value. So I just assumed. I mean, we can have any kind of representation, hashing representation, and we can still have the same sorting. I just felt this is probably nice because I don't like the hashing format and the sorting format, sorting rules are related. But yeah, I mean, if there's any reason to use another encoding, we can have that. It will not fundamentally change anything. Anyway, so this is the table. This is one table. And we have multiple tables because one table is just So this is just like 4 blocks. And so this is how this would go into consensus. So we generate a single block table for every new block, and that goes instantly into the header. And I try to do this drawing. So this arrow shows that we are now like at block 81, and then the table of block 81 instantly goes into the header. And we also generate larger tables. This can be generated by merging the smaller tables, and these are added to the header with some delay, so that we don't have to just so this can be processed somewhat asynchronously, and maybe this is uh, good for processing latencies. And these tables are hashed into a simple chain, because I mean this is good enough. We don't necessarily need uh, some other hashing into with some tree index, with some table indexes. We could do that, but the thing is that in practice, uh, with the small tables, we will only ever need the last few ones. So this is like, yeah, for the hashing, these tables all are hashed into the latest tables uh, representation. But if there's I mean, if a provider wants to prove something, then they will not use the old single block tables because they are less efficient. They will use at most 3 or maybe 4 small tables. They will use like and in the 16 block table row. So this is the third from the bottom. This asynchronous processing is also shown, so that in this case at block 81 we already have all the uh, 4 block tables, and they are being merged into the 16 block table. But it's not added to the consensus yet, because yeah, let's leave some time to process it. And therefore, it's possible that we have to use 4. So we use, in worst case, 4 uh, 4 block tables, and then we can use 16 block tables, and 64 block tables also. And the bigger ones are always more efficient. And in this proposal, I propose that we do not uh, hash bigger tables into consensus, because that would with the requirements for generating this structure is that I mean the initialization doesn't even need any kind of extra wire protocol or anything. You just have to have the last, I think, 80 or 80 few blocks available. And yeah, I think that's a reasonable requirement. uh, and I don't want to require every node to have like a long chain history. Uh, and what we can do, and yeah, I will just get to that also a bit later. We can generate Piggle tables with zk proofs, and this is good because I mean, with zk proofs, if we want to generate the whole index for every new block, that's going to be really expensive and still going to have some latency. So I think for the recent chain history, having these tables in consensus makes sense. And for like the long-term history, uh, it's probably better to just uh, like some bigger infra providers probably can do it even altruistically or share the effort. Yeah, so this is something that uh, still needs to be figured out. But we can use bigger tables also. But I think we should not add them to the headers. And now I will also show how the search and the proof will work, because that's interesting. And yeah, so this example is really uh, the most basic one. So the most basic kind of proof and this is for one table. So I just go back one slide. So the thing is, if we want to search the entire block history, then we will use multiple tables, like bigger ones, and then at the end some smaller ones. But this is just how we prove the existence or non-existence of something in one table. And and the simplest case is when we are looking for something that doesn't exist and we generate an exclusion proof. And yeah, usually this is the most important feature of this whole thing, because inclusion is usually easier to prove than exclusion. And yeah, so this is the most basic case. Let's assume we are looking for a non-existent, some random transaction hash. And what the prover does is it finds where this entry should be in the table and checks whether it's there or not. And this can be done either with a binary search, or probably with a database representation. It's more efficient to just like store a bigger table in chunks, and somehow build a search tree in a chunk level. So like we just check the root chunk and then go after it, loading high level chunks from the database. But anyway, that's implementation detail. uh, so the thing is that it is sorted list, and we can say that there are these two red lines, and we don't see this is transaction hash, but we can find like this would go between these two red lines if it did exist. So what we do is we prove these two entries with a Merkle proof. So yeah, the red three nodes are the proof nodes, like the yellow ones are the reconstructed hashes. And so we have with the logarithmic cost, uh, we can prove that something does not exist in the table. If it did exist, then well, in case of a transaction hash, then probably we don't even really need this table. We could just prove it from the block. But anyways, so if we want to prove, yeah, I will just go to the next example. That will be more interesting. So this is where we also prove like things that do exist. So this is a log pattern query, and we are looking for a USDT transfer from Bob to anyone, and that's our search. And here in this case, there is some room for heuristic optimization from the part of the prover, but uh, I mean, generally, it's a good idea to look for the least popular uh, item first. And and actually, if you have a big search table, and now let's assume we are having search tables with hundreds of thousands of entries, and I think even for 64 blocks, it's realistic to talk about more than 100,000 entries. So yeah, uh, if we are looking for USDT contract address or transfer topic, we are going to have like thousands of matches. But even those, so it is possible to just look up the uh, range of each of these. I mean, we can also assume that the later topics are less frequent, but if we don't want to have such assumptions, we can just check with the logarithmic cost how many matches we have. Like here are these two lines. It's so like we look for address type and the USDT value, and we can just do like this tree search for the first and last entry, and we can already, without reading all the entries, I mean, I'm talking about what the prover does now. So yeah, the prover can determine the number of matches for USDT address, for transfer topic 0, for Bob at topic 1, and the prover can conclude that like the least frequent thing that happens is that topic 1 is Bob, and and here in this case, these four red lines, they prove that that there's exactly these two cases when topic one equals Bob's address. So yeah, block both of them in block 42, and one is in the transaction 0 log 1, and the other is in transaction 1 log 0, which is like actually the second one is the withdrawal. So this is not what we don't want. So yeah, and in this case, it's also good to think in terms of exclusion proofs. So in the end, we are going to prove the actual match, which is like this uh, Bob transfers USDT to Alice. This will be the actual match, the actual result, which is in transaction 0 log 1, and we can prove this through the receipts. And this is also why the block hash is proven, because yeah, so we also proved that this is the block hash of block 42, and this is a convenient way to prove the canonical hash, which might not be so easy if this is an old block. And the prover can use the regular receipts tree to prove this actual match. And what we need to prove is that others are not matches. So just checking topic one already leaves us two options, and we just need to disprove the second one, which is the withdrawal. So yeah, the easy way is just to prove that at block 42 transaction 1 log 0, topic 0 is withdrawal, which is not what we are looking for. So yeah, we ruled out the other match, and yeah, this is all we need to uh, prove a log query in a single table. So yeah, and still, in case of these more complex searches, it's harder to do exact numbers of how expensive a proof is because it depends on some factors. But uh, the overhead, additional overhead over the actual matches, that is still more or less, usually logarithmic. So even if we have to uh, yeah, I mean, anyway, so the bigger tables are always more efficient, and yeah, this is just some reasonings about why I think this whole approach is a good idea, so that we put smaller tables in consensus, and then we prove bigger tables with ZK proofs. So yeah, this is new thing in this whole design, because originally with the complex original EIP 7745, I really tried to achieve that we have a structure that's easy to update, but also efficient for long-term history. But yeah, that comes with high complexity and still some trade-offs. And yeah, so if uh, I think it's obvious that processing very big tables in consensus has some drawbacks, but also if we process everything with ZK proofs, then we don't have the last few blocks or even last few hundred blocks, and for all of these we have to just use the complete block receipts to prove anything. So like if we can generate a ZK proof every hour, which is yeah probably still already kind of expensive, but then just proving the events in the last hour, that will be like 15 or 20 megabytes, which is already kind of expensive. And if we want to like use this whole thing for off-chain or cross-chain event proofs, which I think will be yeah an important thing for future scalability, then this is prohibitive. So even not having the last block indexed is bad. Actually, that's usually the most interesting block probably for these use cases. And yeah, so but if we just process the big tables with long delay, then these proofs can also be built in a collaborative way. Like I have no design for the proofs yet, but I think with this design it's reasonably simple because it's just lists of 64-byte entries ordered, and we have some smaller tables, and we have one bigger table, and we can just generate proofs that prove at certain smaller index ranges that the merge sort is performed correctly. Uh, so actually, it's not going to be a super complex proof. Also, the ZK proof does not need to care about all the receipt encoding and all the stuff because that's done in consensus. So I think this is also with this approach, doing the proofs is also easier technically and also a lot cheaper. So yeah, uh, and yeah, that's pretty much it. Yeah, I still a few things I think we can debate. Like I just said now that okay, let's do 64 blocks tables in consensus, but yeah, maybe we could do more, and then we have even like this whole the proofs will be even cheaper because yeah uh, we have even more time to generate them. But yeah, this is just finding about finding the optimum, and also the hashing scheme. Now I just said that let's use the SSE list merkleization, but we don't necessarily have to use it. And more specifically, I'm honestly not sure about uh, what are the most ZK friendly hashes now. Maybe not SHA-2, but yeah, so we can figure out whether we should use other hash function that's efficient both on CPU and ZK proofs, and also yeah, so this 64-byte encoding in case of SHA-2, I think it's more efficient to use something that's like slightly smaller than 64 bytes because yeah, anyways, these are just minor details. But yeah, so this is my current proposal, and yeah.
Oh, yeah, let me ask a question. So this is now, with this design, not effective to store the whole history and to have
Uh,
provable history.
well, I mean, the tables are effective. I mean, the way I imagine this is that the so the consensus is generating 64 block tables, and yeah, if we can ZK prove bigger tables, we can create tables of million blocks, or I don't know. I mean, this whole thing. If we just always merge uh, two or four smaller tables into a bigger one, the tables does not necessarily have to be uh, power of two sized. I mean, it's just the number of blocks and some events, and the number of events will just be some random number anyway. But it's just yeah convenient to think about. But yeah, so we can keep merging the tables, and in the end we will have a logarithmic number of tables, and we can even have, I don't know, one big table for like most of the old chain history, and few smaller tables at the end. And this, so if we do have big tables, then this is uh, this is significantly more efficient than my original proposal. So I did some I don't have calculations in these slides yet, but in general, if we just um let's just yeah go back on this. What did I? Yeah, here I did some calculation at the like yeah at the end. So proof cost per index table, and yeah, it's for for a ballpark estimate, it's usually a good benchmark to think about just a single exclusion proof per table, and obviously more complex searches will be a few times that, but yeah, so this can be our baseline estimate. And yeah, so proving one exclusion proof is requires proving these two red lines. So with a compact encoding, one entry can be 40 something bytes, and also we have one proof node per tree level. So like this is very small table. So we have like uh, five levels, and if we generate a huge table that covers like most of the history, then and I mean it's a merged sort, so it can be efficiently processed in database and everything. So it's not. I mean, it has some cost, but it's doable. That to generate put most of the history in one table, then the single exclusion proof will be, let's just say, I think the number of these entries is somewhere in the 20 billion range now. So the logarithm of that is 35 or something. So like a single exclusion proof is somewhat like little over 1 kilobyte. I mean, it's not so bad. And that can cover like more than 10 million blocks, or I don't know. And and actually the more expensive thing is if we have these exponentially smaller tables, then uh, the proof cost will increase roughly logarithmically. So let's assume we have like one 35 level table and one 34 level table, and so on and so on, and we have smaller tables, and the full history proof can be like somewhere around 40 kilobytes. And I mean, this is a single exclusion proof. More complex proof can be a few hundred kilobytes. But yeah, I mean, for a full history proof, that's still better than, I don't know, 600 gigabytes. So yeah.
Wait, can I
Hmm.
ask a question?
Yes, sure.
So, so are you saying like this is more efficient than Bloom filters? Um, I just had to ask that, like the
Um,
lookup, because I think my understanding of like Bloom filters, they kind of allow you to like see if, like, it's like kind of like a lookup thing. I'm not sure on like the exact technical details, but I was just wondering like, is the improvement here in terms of like more storing or lookups
This
or?
is less efficient than big enough Bloom filters. The whole thing here is about proving
Oh, it's about proving like inclusion or just
wait,
inclusion, exclusion.
okay.
yeah, so inclusion is usually easier. So this is mostly about proving the complete set of matches for certain criteria. And well, if you're asking about Bloom filters, so well, I mean, it depends on how you use Bloom filters. I mean, the Bloom filters we have now are practically useless. So yeah, it's definitely better than that. Uh, I did some calculations of. I mean, if you have, uh, I no, I really don't think you can even come close to this efficiency with any blow filter based design. Uh, I mean, you could have some huge bloom filter for like many block region. I mean, if you have one bloom filter per block, then you're already way worse because so right now with if we just used bigger bloom filters instead of what we have now in consensus, so like instead of using a 2000 bit bloom filter, we could use something like, I don't know, 100,000 bit bloom filter. So then we would still have like 100,000 bits per block. I mean, yeah, that's way worse than what we have here. So here we can have one table of like 10 million blocks, and we can prove something in it with just 1 kilobyte. So yeah, I think this is the most efficient version I could think of until now. So yeah.
Do
Right.
we have to sort by type?
Well, you don't have to. I think it makes sense. Yeah. So the previous version did not do that. I did that since then. One option is to. I mean,
Well, why I'm asking that? Because I'm asking, can we have this kind of structure and use it as our main log um, storage too, right? So don't have to duplicate this data from the receipts, but kind of unify it with the receipts and store it just once.
well, okay. So yeah, this is an interesting question, and the thing is that uh, yeah, the receipts they so it's maybe probably we have to hash the same data in two different ways anyways. So so this design I mean in this version I dropped that linear log value index thing that I had in previous designs. I mean it has some efficiency advantages, but in this version if we use ZK proven tables and everything, then maybe it's not so important to be the most efficient. So maybe simplicity will help. But anyways, in those designs, I used a separate index entries table. Now I don't have that. So I just propose using the actual receipts for inclusion proofs. So the thing is that so the receipts are organized chronologically. And and probably you also need that. So in this case, now these search values are organized, yeah, by content, and you can look up this. So there's this example like USDT transfer Bob to anyone, and yes, you can look up. Uh, you can look up USDT, you can look up Bob, you can look up transfer, you can match them together, but it will not be easy to find out that it topic two is Alice. So this actual so it will not be easy to reconstruct the actual log because this hashing is organized by content, and now finding something by inclusion position is hard. So I think uh, we do need to hash hash all the events both chronologically, which the receipts do, and also by content. And it's an implementation thing whether we want to deduplicate the actual content. So it is possible to uh, store these tables locally in a way that you don't actually store the type and the value. You do the sorting, and the end you just store the position information, and you can look it up from the receipts. So it's still some extra data to store because it's a different ordering, and yeah, that's what you have to do if you want to more efficiency, but you don't necessarily have to duplicate the actual contents. But I think in any reasonable setup, we do need to hash it, uh, hash them both in a content address way and also or content ordered way and also a chronological way. So yeah, with this design, I think it's best to keep the receipts. Uh, I did have this other version where I had the index entries tree, which did the chronological hashing. So in that case, it would be possible to drop the receipts and have like a different tree representation, but it will still be another way of tree hashing. So yeah, I mean, this is probably the smallest change we can do, and but anyways, yeah, I think it's important to have the two hashings.
Also, quick question. Are these like different tables or is this just one table?
Uh, so what I show in this example is one table. So yeah, but this is so this. I had this example with blocks 40 to 43 with this like 4 events, and this is what I used in all examples. So this is the table, and yeah, if I just switch back and forth between these two tables, then it's obvious. It's just yeah, uh, the difference is what we prove from that. But yeah,
No, I was saying like in terms of like let's say every single like height, is it almost like looking up into a new table? Um,
wait. So yeah, do you have multiple tables? So yeah, there's
so you have the block number table, and then there's a table for log index,
oh no, not
or
necessarily. No, this can be in one table. So yeah, I think it makes sense now. If we do have an index, it makes sense to uh, do all these things, and I think there's no advantage of putting them in separate tables. We could, but putting the type first. This will mean that block hashes will occupy a continuous subtree, and transaction hashes will occupy a continuous subtree. So efficiency-wise, it's almost the same as having separate tables for the different types of entries. But I see no reason to really like create many tables per block. I mean,
Mhm.
yeah, it's just I think easier.
So it's the duplication is not like a problem because like there's a lot of like duplicated values and stuff like that.
So sorry. I mean, every value is duplicated here, but yeah, in the database representation, you don't necessarily have to have them store them twice. It's just yeah, it's you know,
Okay.
it's just the position information that you have to store uh, when it's sorted by content. Yeah, after
Yeah.
sorting it by content. Yeah.
Okay. Okay. All right.
Yeah, still it's probably for the infra providers who want to generate proofs, they will probably I would actually duplicate these values, which is like I mean it has some cost, but if you're running an infra provider node, then what you want is to be efficient, and yeah, if you deduplicate the values, then uh, yeah, you want to generate a proof, and you have to like look up all these values from very different places, and it's not super efficient. So if you want to be efficient at generating proofs, then I would say probably it's best to just duplicate it. But I mean, if you are running a node for this purpose, then I mean it's an affordable cost. Uh, and for those who don't want to generate like long-term history proofs, just I don't know, generate the consensus stuff, they really don't need to deal with big tables. So those who just generate the consensus can mostly just keep those tables that have non-finalized parts. So all the finalized tables can be discarded if you just want to generate the consensus. So then then the storage efficiency is really not an issue. And yeah, if you want to use it, then probably you don't you can just duplicate. Maybe if you want to use this structure locally, just for local search, then you can, because you're running your own full node and you just want to uh, uh, search for yourself, then you can generate these tables for yourself, and you don't even need zk proofs because you know they are correct because you generated them. And then maybe for local use it might be a good compromise to store the final tables with just the position info, and then the lookup is a little bit more expensive, but the whole structure will not cost another 600 gigabytes, more like, I don't know, less than 100. So yeah, I mean, the index does have some cost. If you want to index the entire history and do quick lookups, I mean, it will have some storage costs, but yeah, it's optional. Uh,
All right, thank you. I think I'm gonna hop off.
all right. Okay, thanks for coming. Yeah. Okay. Anyways, this is pretty much what I wanted to talk about today. Any more questions?
No, thank you.
Okay. Then I think we can call it a day. And yeah, by the way, just for the quick feedback, um, do you how do you relate to the complexity of this? So does it sound very complex, or now does this sound like something manageable, more manageable?
No, I don't know. Complex is put some attention, but it's so comprehensible.
Okay. All right.
Um,
Okay. So okay. So should we call it a day then?
No,
You
thanks.
have more questions? All right.
Thank you so much. Bye bye.
Thank you. Bye bye.